co-hosting privileges in case they feel like sharing their slides during the
Oh,
questions?
no. Anybody can slide. Yeah,
Oh, okay.
Anybody can. Yeah,
Perfect.
anybody can share slide. Yes.
Fantastic. Okay. So yeah, welcome to the panel discussion to conclude the day. I'm just looking to see who's present. So if all the speakers of today's sessions could turn on their cameras, we're probably going to keep it, sort of actually simulate, being on a physical panel. We have an additional guest. I'd like to announce that we have an additional guest for the panel session. Enrico Payer has very kindly agreed to be present and to join the discussion. Initially, we were worried that Jérôme Martin, is he here? Jérôme? It's Bastille Day in France, where Jérôme is physically present, and so others. And before we get going, I should stress that the panel discussion is set for 50 minutes. Of course, if there's a particularly lively discussion and we feel like going over, the organizers have given us the blessings to sort of continue informally afterwards. So you can view that as sort of coffee and tea after the conference, or maybe even after row. But we will try to formally conclude after 50 minutes. And I thought it might be useful to sort of group the speakers into sort of so it's not all 8 speakers sort of answering questions at the same time, and we'll sort of work through the different groups. And I thought it would be nice to sort of group Jérôme, Enrico, Zhengji, and Rishi. Although Rishi, I wasn't quite sure whether you belonged in this category. I mean, this is loosely sort of early universe initial conditions, CMB related discussions. And then I thought another group would be, a natural group would be Pedro, Mark, and Emma. And I don't see Anupam, unfortunately, but I thought Gianluca and Anupam could be a coherent group because you're both interested in questions of quantum gravity. But is Anupam here? It doesn't appear that he's here. Okay, so maybe just because Gianluca, you're sort of now in a category of your own, I thought we could just kick off the discussion with your talk. So it's very interesting stuff. I very much enjoyed hearing about all the different phenomenological approaches you've been taking to understand the question of what, if any, quantum gravitational effects can be hoped to test and constrain with gravitational waves. I have a few questions, but if anybody else has a question they'd like to ask Gianluca, please just go ahead and ask away.
Yeah, I wanted to ask a small question. That is that, so in any of the quantum gravity theories, do you have a parity violating term? Because that can show up as we had discussions in many of the talks. That can show up as chiral gravitation waves or chiral 3-point functions.
Yeah, there are some models which realize a parity violation in several ways. One is actually to add the parity violating term in the nonlinear action for gravity, a Pontryagin-like term. I don't know how much these models have been embedded in a full theory of quantum gravity. But I mean, even in Mark Kaminkowski was one of the first to propose parity violation terms, and I think also Chern-Simons gravity should have some parity violation effect. But as far as I know, I understand these are more like models built with a purpose of finding parity violation signal rather than something which was found more or less accidentally in a mature proposal of quantum gravity. So I would say that those models I've talked about in my talk in general do not lead to parity violation. Okay, but others do, but on the other hand, they do not maybe they do not give rise, I don't know, to blue tilt spectrum or to deviation from the standard luminosity distance. So it's I would say that there are complementary fields of research. I don't know if this answers.
Yeah, I think yeah. This is something I wanted to ask. Yeah, thank you.
So Gianluca, I was curious about at the very beginning of your talk, you discussed modified dispersion relations, and you in particular looked at a particular functional form. And so, and correct me if I'm mistaken, but my understanding is that as soon as you modify dispersion relations, you are also breaking standard Lorentz invariants, presumably by the effects of higher dimensional operators that become relevant at a particular scale. So my first question is that a correct understanding that indeed that it is a Lorentz violating thing that you have to assume is restored at low energies? And then my next question is, did you make sure that you don't have any unacceptable low energy consequences, because it's actually quite difficult?
Not necessarily, because you can have, for instance, higher derivative kinetic terms as the powers of a D'Alembert, and that doesn't break Lorentz invariance. So if it really depends on what type of dispersion relation you consider. You can have a highly modified dispersion relations which preserve a Lorentz invariance or not. When you break a Lorentz invariance, of course, you have to take into account many things, but I have to say usually are not taken into account. One is that people often limit discussion to classical effects of Lorentz violation. But if you have a quantum field theory with Lorentz violation, in general, loop corrections enhance this violation, no matter how small it is, enhance it to the level of %, which is phenomenologically unacceptable. This is a classic argument by Collins and collaborators, which killed a great amount of theories, including Horzavalich's gravity in its first formulation suffered from this problem. So acceptable Lorentz violation at the classical level, but then amplified at the quantum level. I would say in general, Lorentz violation is it should be considered at both levels if one wants to be on a safe side. Among the models I briefly went through, those with multifractal geometry in general do break Lorentz violation, do break Lorentz symmetry, sorry, in the UV, and it is recovered in the infrared. And there, well, at the quantum level, you don't have this amplification of Lorentz breaking. But on the other hand, those theory are not really completed theories of quantum gravity either. So the problem is still standing.
I see. Thank you. If anybody else has any questions for Gianluca?
Yeah, just to follow up on this. So this D'Alembert operator you talked about, I mean, they do break a causality at some point of time, right? Even in the UV, even if you can maintain the Lorentz invariance, I think at the microscopic level you're still violating causality. So does it somewhere show up in your I don't know, I mean, gravitational signals or some other way?
Sorry, I couldn't hear you well because there was like some wind in your microphone.
No, sorry. Yes, sorry. I know. I was just saying that the powers, I mean, the transcendental functions of the D'Alembert that you showed us. So they do violate causality, right? At the microscopic level, since you have D'Alembert, so you're only affecting one of the I mean space-time components. So I believe you're also violating causality at the microscopic level.
Which theories? I mean those with asymptotic polynomial or exponential operators, yes, they violate microcausality, but they don't violate the macrocausality. And for instance, there is no Shapiro time delay in Nervoso theories, so it's a safe or safe.
But this might, but is it any way to get any signals of gravitation away from this microscopic level causality violation in the UV? If I think it like a UV
as far as I know, no, not in no local quantum gravity. If you look at quantum gravity with infrared modifications, then you may have something, because, for instance, in that class of dark energy models, well, I proposed in one slide, I mentioned quickly, when the power of a D'Alembert is non-integer, you violate the Huygens principle, which means that signals can propagate slower than light. You don't have superluminous signals, but you have a subluminous signals. But it's not clear whether these signals are physical or it just applies, looking at the very retarded and advanced Green's functions, which are well-defined mathematical objects, but they still do not represent the propagation of physical signals. So it's not clear whether you would have such an effect, an observable effect. I don't know.
I wanted to make a comment about this this quantum gravity, that one of the kind of at a very naive level, a simple obstacle is the friction or the tension between renormalizability and unitarity. So on the one hand, you would like the propagators of the graviton to give you a lot of suppression in the UV, so you become power counter renormalizable. But on the other hand, if you do that, you violate unitarity bounds on the scaling of the propagator. So in general, unitarity, I think, is an important point to ensure that it's satisfied by every theory which has the ambition to at least even describe gravity perturbatively. And I thought I would mention that because much phenomenology is actually constrained by those simple observations, just by unitarity itself. And since we were discussing before about parity violations, there are certain things that you wouldn't expect, but because of unitarity that they happen. For example, if you were to compute, do a calculation similar to what Mark was discussing for these parity violations, but you think, well, I want to compute also the 3-point function or the 4-point function, and just to see what they look like, you would discover that almost all possible parity violating interactions give you exactly 0 effect in correlators. And that would be surprising, but it's a direct consequence of unitarity. And in fact, there is only a handful of operators that can respect it. So I thought it's kind of important to keep, when we're discussing more phenomenological proposals for theories of quantum gravity, it's important to keep those constraints in mind, to make those at least viables as a low energy effective description.
Yeah, of the two non-local theories I showed you in my slides, the one with fractional D'Alembert does not have a unitarity normalizability at the same time, unfortunately. That's actually was the subject of my papers. Well, the first one on scalar field, where I showed that. Well, let's be more precise. It's not power counter normalizable, but it is one loop finite. So power counter normalizability is a necessary condition, but it's not sufficient. So if a theory is not power counter normalizable, it doesn't mean that it's not renormalizable, because the cancellations can happen. And in fact, they do happen even in general relativity or in supergravity. So power counter normalizability is not the end of the story. When it fails, and you can do the calculations, you may get nice surprises. And in fact, that's what happens for this theory with fractional D'Alembert. However, I could calculate only up to one loop, so I cannot claim anything beyond the one loop. Okay, so that's the issue there is open. On the other hand, the non-local quantum gravity with asymptotic polynomial or exponential operators is a unitary and power country normalizable at the same time. So, and the reason is that those local operators basically cure the unitarity problem of Stelle theory. So having a higher order Q vector terms improve renormalizability, but in general violates unitarity because it introduces higher order derivatives. But the insertion of those form factor, no local form factors preserves the unitarity and also incidentally also improves renormalizability.
When you say improves, do you mean that it is power counting UV finite to all energies, or it just extends the cutoffs to some?
It means that depending on the dimensional space-time, the theory becomes a super renormalizable or even finite, and can be made finite if you add to your bare action some local operators, which are called killer operators, which can make the theory even finite. But the key point is where the main effect on locality is to improve, is to preserve unitarity. So they don't introduce extra degrees of freedom. I agree with you that in general, one should consider both issues. The point is that many theories of quantum gravity are even formulated at the non-perturbative level. So it's not even, you cannot even talk about perturbative renormalizability because it's just not the game they're playing. So it's and about unitarity, I think that's also something which is still very much work in progress. I tried the models I showed you, for instance, for the stochastic background, where the best I could find in the literature about the stochastic gravitation wave background, but there are many more theories of quantum gravity, even much more rigorous than models, those models I discussed there. But on the other hand, they do not reach the point of having phenomenology for cosmology or for gravitational waves.
Yeah, that's the tension. I just wanted to make one comment that paraphrasing Mark's talk is that if a theory is not power counting renormalizable, we should assume that it is guilty until it is proven to be innocent.
I disagree. I mean, the lesson of gauge theories, supergravity and general relativity prove that cancellations do happen.
Cancellations do happen, but even in supergravity, which has a lot in n equals 8, a lot of supersymmetry, you don't know that it is finite to all number of loops. So, I mean, the lesson is that at up to 7 loops, maybe you have cancellations, but even there, that you have a huge amount of symmetries, you doubt that it is UV finite. I think it's
yeah, where the issue is a kind of opening of there are these little theorems, but I would.
No, I was just going to say, so maybe we could pick this up informally after,
Okay.
you know, at the end of this, just because I do want to get all the other speakers in. I mean, these are interesting points, and I'd be very, you know, if you can stick around after the formal thing's over, we can continue. I think these are some very important points. So I just want to cycle over to the next batch of speakers. So I mean, you know, very loosely, just thematically, I thought Pedro, Mark, and Emma would be a very natural sort of a sub panel to sort of discuss with over the next 20-25 minutes. So if you have any questions for any of those, either Pedro, Mark, or Emma, please just unmute and ask, or I can kick off the discussion. But if anybody has any questions or comments or anything you found interesting about these talks.
Maybe
So,
I can ask if nobody is have any questions. So again, my question will be related to the chirality. So my question is to Pedro. Is that so usually we do not simulate fermions in the lattice because we believe that's going to be a Pauli blocking and the energy density coming from that not going to be I mean dominant enough. But can there be cases, especially in the cases of action where you have a derivative coupling, can the fermion production be I mean significant enough to be considered in your sinter simulation, and especially as a back reaction? And then how much can you, how much do you expect this to happen? And then, of course, if the fermions are like Sand model, they're chiral, the signals can be chiral as well.
So yeah, it's a good question. Yeah. So I think the derivative coupling should not change anything about the Pauli blocking. Yeah. But I think at least I read that in the chat before that this is what you were asking about. And I think in general, yeah, you don't get this this runaway behavior. You can, I think, on very steep potentials, you can get enough friction from fermions also. And there was, I think, for the relaxion, there was a model looking into it, but it looked to require very weird parameters in the sense that you had like a coupling or a coupling scale for the coupling to fermions had to be much larger than the one to the bosons. So it seemed a bit unnatural to me. We tried to understand if we can get this using a clockwork mechanism. So I think at least for inflation, people have tried to do this. I haven't looked much into it. Maybe someone else has a better answer. Okay, at least no one disagrees.
So Pedro, I wanted to ask you about just a general idea that we expect from various theories that there's the possibility of axions in general. It's not a forbidden thing to exist in any effective theory. So if you go sort of from the sort of the string inspired perspective, that actually we expect a lot, like quite a lot, right? So you looked at the effects of like 1 or 2, either U1 or SU2 gauge fields. So wouldn't having if you like a string axiverse type scenario result in a string axiverse of orbital axions? Because the argument seemed quite general, right? In that case, wouldn't that generate a humongous stochastic background? Or is that too naive?
Well, I guess you're right in principle. Yeah, I mean, the one thing that I didn't stress much in my talk, because it's a little bit ugly, is that we need a large coupling of the axion to the gauge fields. Yeah, so there's a parameter that I think it starts around 20 or so. Yeah, so you can imagine you have a bunch of charged fields in the loop or whatever, how you generate that coupling. It's not terrible, but so if you take your axiverse, maybe not all of the axions would have such a large coupling. Yeah, you can arrange it. If you have 2 axions, you can arrange for one of them to have a enhanced coupling or something like that. Yeah, but then of course, yeah, I mean, you can do this. Yeah, you can add the signal we computed for radiation domination. You throw in 20 axions, a variety of initial conditions, and so on. Yeah, and I guess even I think there was a paper because there's some non-trivial dynamics that axions have by themselves. If you take into account that the potential is not m squared phi squared if you go far enough from the origin, and then there are all these oscillons and so on. I think that kind of dynamics also does give rise to gravitational waves. I think there was a paper from at least one Japanese group, I think, that is about the string. Yeah, the gravitational wave forest of the string axiverse, I think, exactly looking into this idea that you just mentioned. Mm-hmm. So yeah, it's something that one can consider. That seems at least not unreasonable. Yeah.
Just a small follow-up on that. So you talked about large couplings of action to gauge fields, right? So in a scenario where you have large number of flavors or large number of gauge fields, I mean, that runs in the loop and the action couple. So you can have the effective coupling is large enough, but the tree level coupling that you can imagine with an action to this flavors, I mean, many number of fermions or which runs in the loop can be small enough, right? So in principle, like it's an effective coupling in any case, because you have to write a dimension 5 term. So maybe when you write a complete model, it is possible that those couplings are small enough, but you have a large number of flavors, which can, I don't know, I'm just saying this is just a natural way of understanding large effective couplings, I think.
Yeah, I agree. I'm just saying it's not, you know, typically when you do EFT, you write a 1 for the coupling, or you put a coefficient, say this is a number order 1, and then I show you a plot where I take this parameter between 40 and 100, because that's where the interesting stuff happens. But it's, you know, yeah, it's possible to write down a model, and the model doesn't have to be sick, but it's not super elegant, I think, at least. And if you imagine that those couplings are somehow randomly generated in your model space, then yeah, maybe you wouldn't expect all of them to have a very large coupling. I don't know what the generic expectation from string theory is. Yeah, maybe there you also have some reasoning of for why some of the couplings could be larger than others. I mean, there might be some geometric factors, but I don't know much about that stuff. Yeah, I mean, from a pure EFT perspective, yeah, of course, you can do whatever you want. You can build an arbitrarily nice signal by combining phase transitions and audible axions and whatever you want.
One more point, if I may. So the plot that you showed in the parameter space of, I think, 1 by f versus the mass of the action, you showed that there can be some regions which are favorable for laboratory and astrophysical searches, and then there are some regions below where the gravitational wave from BBO and this kind of scenarios are covering. So is it possible? I mean, I think the reason why this is the gravitational wave are very far below and it's not going up, I mean, maybe to the regions of complementary to regions with the lab, because you need a very high value of FA, right? Am I correct? Because that is when getting. So is it possible to imagine a model of action cosmology where you can bump up? I mean, this white region, the huge white region which you have in your plot, can be covered by gravitation wave detectors, and we can have maybe complementary regions in the same parameter space.
I can show this briefly again so that everyone knows what we're talking about.
Yeah, yes. This is exactly what I'm saying. Yeah.
And then, so I think, I mean, we have kind of explored. So in the simplest model that we are considering, yeah, the axion starts to roll when the Hubble rate becomes of order of its mass. Now that's just what the equations of motion tell you. And at that time, you can compute the energy density that is in the axion, which is simply the mass squared times the field value squared. So this is m squared f squared, because you have an order 1. Yeah, your typical expectation for the field displacement is order 1 number times f. And then you divide it by the radiation energy density, which is yeah, and this is where you get this F over M Planck suppression. So in the simplest model, this is what comes out. Now, one of the ways to cheat your way out of this, if you want, sharing is paused. Why is sharing paused? Bring your shared window to the front. Okay, maybe it doesn't matter. So, I mean, the one thing I mentioned is you can give your field a lot of kinetic energy instead of using the potential energy, and then you become independent of the coupling or of the scale. Yeah, so this means you can get a gravitational wave signal for smaller values of the decay constant. And the other way that we explored, and this is what's built, what happens in fact in this relaxion model, is that you can try to delay the onset of the rolling. Yeah, because so imagine if you put a stop sign in front of the axion, so you cannot roll yet. As long as it's stuck at a displaced field value, it behaves like a cosmological constant. So it will keep increasing relative to the radiation bars. And this is what happens effectively in the relaxion scenario, where you kind of kick the axion late after it would normally have already settled. And yeah, I mean, both these things work to give you a detectable signal away from this region that of very large decay constant.
Are there any questions perhaps for either Mark or Emma? So Mark, I had a question about a particular slide in your talk where you were sort of looking at the effects on galaxies, galaxy shear of gravitational polarizations beyond the usual two that we expect from the transverse traceless gravitational polarity. So ordinarily that would come, I imagine. So, well, actually, no, maybe I'll just ask you a question. So where would they come from? Where are these other polarizations coming from?
That's a good question. I don't have a good answer. The standard transverse traceless polarizations can come about in models of inflation in which there is a tensor scalar coupling. And presumably those other polarizations could arise in models in which there's some vector field that couples to two scalars. It's hard to actually construct a model that does so. I don't have such a model, but that's what it would require. It would require a vector scalar coupling.
I see. Okay, yeah, because I was just wondering if you had maybe massive gravity in mind or something like this when you were.
In principle, but getting the vector modes and massive gravity theories to couple is kind of tricky.
Right.
Getting the scalar modes is a little easier in terms of theory. It's easy to construct models with an extra scalar degree of freedom that can couple to the inflaton.
Yeah.
So Mark, you said there were 5 degrees of freedom, but that in the next slide you showed 6 different modes. Did I miss something here?
So that sixth mode is a scalar mode. It's analogous to, it's essentially the same calculations when you do cosmological perturbations and then fix the gauge. There's 6 degrees of freedom. 5 of them can be arranged into a traceless symmetric tensor. And then the other one is a scalar mode. So if you remember the picture, I might be able to show the picture. One of the modes does not involve elongations, just there it is. So there are 5 modes that involve ellipticities. There's H plus, H cross. Can you see this?
Oh, yeah.
There's H plus, there's H cross, the standard transverse traceless modes. So what happens in this case is that there is an elongation transverse to the direction of the Fourier mode.
Yeah.
And for the plus, it's in the XY plane, and for cross, it's on 2 planes that are rotated by 45 degrees. There's then 2 vector modes in which there's an elongation that varies along the direction of the gravitational wave, or the direction of the Fourier mode, where the elongation is in a plane defined by the direction of the Fourier mode and then either the x-axis or the y-axis. And here, the variation of the elongation is along the direction of the Fourier mode. But then there's another possibility, which is that the isocurvature, the isocorrelation contours remain spherical, but simply vary in space. So this is a scalar mode, and these other 5 are the 5 the 5 symmetric trace-free tensor modes. So
Okay. You also mentioned a bit further on that chiral gravitational waves can end up sourcing chiral CMB photons, and is that because they have a common origin, or is that because of graviton photon scattering would sort of induce one of the photons from graviton? So, is it a common origin effect, or does one induce one of the other? I just missed
one induces the other. The gravitational wave, the circular polarization of the gravitational waves gets imprinted on the circular polarization of the photons. And
so that must be quite inefficient, though, right? Or
yeah, it's a very, very small effect. It's order alpha squared and the fine structure constant alpha.
Yeah.
And then it's the amplitude of the gravitational wave, which at most is like 10 to the minus 6.
I see. But I suppose if CMB photons are expected to not be circularly polarized, then you have a null test, and if you see something, is that the picture that no matter how small the effect is, that looking for a zero?
Yeah, in principle, but it's essentially an academic exercise because it's like the circular polarization amplitude is about 10 orders of magnitude smaller than what can be detected, now or in the short-term future. But there's the prospects for 21 centimeter circular polarization are better. We just haven't finished the paper, but
41 centimeter will have many other sources of circular polarization, I guess. There are magnetic fields during reionization that will give you.
yes, although I don't know if they've been calculated.
I think Tejasvi had calculated something. Tejasvi, Venu Madhav and Hirata had some papers about that. Oh no, that was Zeeman splitting.
Yeah, that was not circular polarization. I think that was linear polarization.
But still, I would think that it is coming from this reionization, and there are stars and galaxies, and there should be magnetic fields. There should be some.
Yeah, but nothing that would produce an isotropic circular polarization. 21 centimeter photons, yes, they may well be circularly polarized, but having a circular polarization that's uniform across the entire sky would be requires some type of parity breaking.
So if I may, so since this 21 centimeter and the CMB, so the tail of the CMB basically is like the region of 21 centimeter. So probably my question is to Subodh. So will there be any prospects of doing it with the mu distortion as well? I mean, we can have some, because we are talking in the same frequency region, right?
I'm not sure. I mean, if it happens to be in the same frequency region. So what was the question? Like whether you have any
no, but my question is that if we have a stochastic source of this circularly polarized gravitational waves, then does it have any effects on the mu distortion?
I mean, anything that gives you tensor dissipation will give you
signal,
right? So whether you can disentangle the effect of circular polarization from
and also if the effect is large enough, if effect is large enough.
Yeah, I mean the transfer function for tensor modes to mu distortion is going to be dwarfed by scalars. So if there's anything around that's doing the same thing in scalars, that's going to be the dominant signal, for sure.
So I don't see how there's going to be a signature of parity breaking in a mu distortion.
Yeah. And also the same for tau distortion as well, right?
Yeah, I think so.
Yeah. I just wanted to get in a question for Emma. So you mentioned in your slides the possibility of blue tilted gravitational wave spectra. Are you imagining these to be from vacuum fluctuations or not?
So The blue tilted, really, I didn't show an example. I didn't show a concrete model.
Yeah.
And I was mostly making a point that in order to see gravitational waves from a small scale, you need a blue tilt. The models that I was considering, they mostly generate this bump. And so it can be different scales, I guess. If you are if you're looking at the range of frequencies where the bump is descending, it could appear as a blue tilt, but but the general prediction is a bump for the specific model that I was discussing. Yeah.
Okay. Yeah, because I just want, because anything that's blue tilted has to cut off at some point, and then for normalization actually subtracts quite a bit of. I think there's some models out there that think that you have a blue tilt that goes on forever. Need to take into account normalization correctly, but is the reason you focused on? Is the reason you focused on SU2 fields as opposed to U1? Is there like some strong coupling? There's some noise in the literature about why SU2 is actually somehow more under control than
it is. So it is.
A bit on that.
Okay, okay. People working on the U1 will tell you, that all the nice things about the U1 model. But the thing is about the SU2, I think there are two things. One is that you have linear production of gravitational waves. So that kind of channel you cannot use to produce the density, the curvature perturbations. So in a sense, you are decoupling the production of gravitational waves from what goes on in the scalar sector. Now that is not still the gauge fields are gonna enter into the dynamics of the scalar factor in some way, but not in this with the same exact channel. On the other hand, that's what happens for the U1. You have the same exact channel, so you are in a sense more constrained because the same channel is sourcing both scalar and tensors. So I guess this is the main difference. Maybe people can argue that you can have less back reaction in these models. For example, there are some works by Eiichiro and collaborators where they consider back reaction, considering additional fields to see if you can have basically ruin the gauge field production. And apparently the back reaction can be stronger for the U1 as opposed to the SU2, and that's because the SU2 have a mass. So that's another. But okay, it's not an absolute argument in favor of the SU2. I think the phenomenological argument is probably the most convincing if one wants to pick between the two. Yeah.
Are there any other questions for Emma, Mark, or Pedro before we move on to cycling and Jerome and Rishi? So we lost Zhengji. I believe it's quite late in China at this time, so that's where Enrico had to depart for childcare reasons. And we did begin 10 minutes late, so we're going to finish 10 minutes later than the schedule. And then, like I said, if there's any sort of informal discussions you want to have, I still have some questions I'd like to ask some of the speakers. If you can stick around, that'd be great. If not, just feel free to leave. So maybe we could cycle in Jerome and Rishi, if anybody has any questions or comments about their talks. So Rishi, I found it to be a very interesting claim that if you allowed for neutrinos to have some non-trivial interaction with dark matter, that you can basically resolve some aspect of the Hubble tension. And you showed these sort of rather dramatic plots where it sort of shifts quite a lot. But surely that must depend on the cross section, right? And so what cross section do you actually need to get complete resolution of the Hubble tension just from that interaction? Yeah, and does it come into conflict with other phenomenological bounds?
Okay, I don't remember exactly. It was, I think, of order of Thomson cross sections. But we checked that there are no other constraints. So it is still within all collider bounds. So the constraint, yeah, so cross section has to be high,
Mm.
and it has to be of order Thomson cross section.
That's quite a lot. It's still a huge.
Yeah. But it is between neutrino and dark matter.
Yeah.
Usually there are not really any constraints which constrain this kind of cross sections.
Okay.
And actually, it has to be only a neutrino and a very small fraction of dark matter. So interacting component of dark matter is 1 part in 10 to the 3.
I see. I see. Okay.
Yeah.
And
You
you
cannot have
managed.
neutrinos interact with all of dark matter,
Yeah.
because that will create a radiation pressure and then acoustic oscillations in dark matter, and
Yeah.
everything will break down.
So you managed to do this not just resolve the Hubble tension as far as for CMB observations, you also still
Yeah,
BAO.
we checked all other constraints from collider or astrophysics.
But what about BAO? Did you manage to fit BAO just as well with this interaction cross section?
Yeah, BAO also it matches. So BAO, the effect will be same thing. That's the same phase shift that you have in the CMB that you will have in BAO also. So the Hubble that you get from BAO will also move to higher values.
I see.
So it consistently resolves the Hubble tension from CMB and BAO. It makes it consistent with the local. Yeah. So I showed you only the best constraint, which was 2.1. So you decrease it to 2.1, but it depends on what data sets you choose. So if you go to slightly nonlinear scales or linear scales in the matter power spectrum, so it moves around between 2 and 3 sigma. But we consistently manage it below 3 sigma, so we push it down below 3 sigma.
Yes.
Just if I may say here, so the dark matter neutrino cross section that you are talking about, is it not going to be the same as the neutrino floor of the dark matter direct detection experiments, which is roughly 10 to the power minus 50 centimeter square, I think. So it's that is what we are
neutrino floor
looking
is coming
at.
from neutrino interactions with baryons.
Yes, so it's not the
I'm
same.
talking about neutrino interacting with dark matter.
I see. Okay. So the constraint is different. Order of scale is different. And in your case, does the result also depend somewhat on the prior that you choose, like whether you use some? I mean, does the result have some dependency on what kind of priors that you use in?
There is no prior. It's just you just fit to the CMB data and matter power spectrum.
Yeah.
It appears we lost Jerome because he had to go. If I'd known he was time restricted, I would have actually cycled him before. We're getting close to the formal end of the discussion session. So at this point, I think we can just sort of have an informal discussion. Yeah. So Rishi, I think I missed the point. I think you had 2 parts to your talk as well, and in the earlier section you were talking about neutrinos being essentially being able to mimic a blue tilt in the B mode you would have gotten from inflation.
Yeah, so it is the same interaction which solves the Hubble tension.
Yeah.
So you ask what will it do with what we are doing is stopping the neutrinos from free streaming. That's all we are doing, and we can ask what is it doing to the scalar modes. So in scalar mode, it solves the Hubble tension. And you ask does it do something to the tensor modes? And the answer is yes. So the free streaming neutrinos, they damp the gravitational waves.
I see.
And if you stop the neutrinos from free streaming, then the damping goes away. So what this damping does is it suppresses the gravitational waves on small scales.
Mhm.
So the gravitational waves that we observe, they are no longer scale invariant. Actually, the Moores which entered before matter radiation equality, they are actually suppressed by 50% compared to the Moores which entered during matter. This is like silk damping. This is the dissipation, just like silk damping. But the anisotropic stress in the neutrinos, it just vanishes because neutrinos are free streaming.
See.
If you stop the neutrinos from free streaming, then you don't have this damping. So this scale invariant power spectrum coming from inflation remains scale invariant. So if you compare to the free streaming scenario, then you have boosted the power.
I see.
Basically, free streaming neutrinos with a blue initial spectrum is equivalent to non-free streaming neutrinos with scale invariant spectrum. So tomorrow, if you observe blue spectrum, so you need not rush to conclude that inflation is wrong because your spectrum is blue. It could just be. We were trying to see if you can get some other information from CMB modes, some BSM physics if you can constrain.
That underestimates the amount of which inflationary model builders are creative, and there's all sorts of ways people can get the long story out of it.
That is fine. So I was just thinking, if you have take the simplest single field inflationary models, then you expect. So if you detected a blue spectrum, you would conclude that inflation is much more complicated, or the simplest models are ruled out. That need not be true. It could just be the post-inflationary physics that can change the. So basically, the point is that post-inflationary physics can modify the spectrum of gravitational waves. In the same way that inflationary BSM physics modifies the spectrum of scalar modes and CMB, and if we use CMB power spectrum to constrain all kinds of new physics, we can do same thing with B modes also. If we can measure it, with same precision that we do the scalar modes.
Okay, I think this is probably a good time to conclude the formal discussion session. So you can just stop recording and we can just continue having an intro. So Gianluca, I was just wanting to ask you again about